So let's go into our next major topic. So this is my favorite topic of the course, spectroscopy. It's a family of techniques that can be used to determine if a chemical is present, or to identify a chemical, or to quantify a chemical. So there's our two major questions in AChem, right? What do we have and how much? Now there are a variety of spectroscopies out there, but they all come down to using light to learn about a sample. And so before we even talk about the techniques, we need to review some concepts regarding light and orbitals. But unlike earlier concepts, I am only going to spend this one lecture on review, and then we're going to hit the ground running with AChem. Alright, so we're not going to get too much into the physics of light, but it does help to have some idea of what it is. And I'm going to start by presenting a series of visuals, and then we'll write down the most important points afterwards. So don't write this down, but at some point you should have seen light represented in some class as a sine wave. So why do we represent it like that? Well, you have to have some understanding of how light is created in the first place to appreciate it. Light is created by a charged particle oscillating in some periodic motion while releasing this radiation that we call light. Again, we're not going to get too deep into the physics of it, but just to give a crude visual of what I'm describing, imagine we have this charged particle here, and it's about to move up. And as it moves up, it emits this radiation. It kind of looked like it was just leaking out this radiation here that we call light. And then it moves back down, because again, this is an oscillating motion. And it continues to emit this radiation, and thus we build the first crest of our light wave. And if it keeps on oscillating up and down, it will continue to release this light. And because the particle is moving in a consistent periodic motion as opposed to something random like this, we get this consistent repeating pattern here, which can be described mathematically with a sine wave. And to be clear, these are not four different light waves. This is one light wave with four crests or peaks. And the distance or length between two peaks is what we call the wavelength. And that term should certainly sound familiar to you. We'll write it down later. First, let's just address how wavelength relates to another important concept, frequency. Frequency is just how many crests can go through a point per second. Instead of using the word crests, we could also use the word periods, which just translates to how many repetitions go through a point per second. Since, as discussed in the previous slide, these waves consist of repetitive patterns. So we have to note that all light travels at the same speed, regardless of if it's a radio wave or an X-ray. What can change is the distance between two peaks or crests, in other words, the wavelength. And there's an inverse relationship between that wavelength and the light wave's frequency. And so we're about to see two different light waves travel at the same speed through this line here. But the one on the bottom will have half the wavelength of the one on the top. Here we go. And so we can see that in the same amount of time, twice as many crests in this wave were able to go through this line here compared to this wave, where the wavelength was twice as large, and thus the frequency was cut in half. And so to finish off our light radiation basics, in addition to having a wavelength, a light wave has an amplitude, which is related to its intensity or brightness. The amplitude is not such a relevant concept in this class, but wavelength is extremely important, and we already saw that it's related to frequency, and we can tie it in with the speed of light with this equation here. The speed of light is equal to wavelength times frequency. And in a vacuum, it is equal to 2.998 times 10 to the 8th meters per second. Or we can use that inverse second unit. Sometimes in spectroscopy equations, inverse units are a simpler representation. Now I say that this is in a vacuum because if light is traveling through some substance, it will become slower. But in this class, we will always just use this number by default. And so wavelength will be in units of meters, and frequency will be in units of inverse seconds, or we can just call that hertz. And so quickly pause the video and write all of this down, and then I'll write some notes underneath that. Okay, doing a quick rearrangement of that equation, we can bring the wavelength to the other side and say that C times the inverse of wavelength is equal to frequency. And then we will redefine that inverse wavelength as something called the wave number, which has the same symbol as frequency, but with that little symbol above it. So C times wave number equals frequency. And so let's define that wave number. We commonly see this in IR spectroscopy, which you should have done if you've taken Orgo Lab. If you haven't, that's fine. We'll just say common in IR, and we'll talk about that more later. Because it's the inverse of wavelength, our units are going to be inverse distances. And while meter to the -1 is technically right, conventionally we almost always use inverse centimeters. And now for an extremely important equation for this whole topic of spectroscopy. Let's star this. All light radiation has an energy associated with it. And the energy of that light can be related to its frequency through this equation. H, which is a constant we'll define momentarily, times frequency. H is known as Planck's constant and is equal to 6.626 times 10 to the negative 34. 6.626 times 10 to the negative 34, and the units are joules times second. But we also know from this equation up here that wavelength and frequency are related as well. And so the much more common way of writing this equation here, at least in this class, is energy is equal to hc over wavelength. And then one more iteration of this equation, hc over wavelength is the same as saying hc times the inverse of wavelength, which is just the wave number. So we could write this as hc wave number. And we'll utilize all of these forms in class, but without a doubt, this is the one we'll see the most. But to understand how we use these equations, we first need to review orbitals. Okay, so we should have some memory of learning about these in Gen Chem, but let's just review the most important points for this topic. First of all, an orbital is the region where an electron is roughly 95% likely to be found. Orbitals come in different shapes and sizes that have different labels. So for example, we should recall there's something called the s orbital. An electron that's in an s orbital occupies a spherical space around the nucleus of an atom. And we have this number called the principal number that goes in front of it, like 1s, 2s, 3s, and as that number becomes larger, the spherical space that the electron can be found in becomes larger as well. But there are also orbitals known as p orbitals that have these dumbbell-like shapes and exist in different orientations. And they can also increase in size with this principal number. And then there are d orbitals, which we're not even going to touch in this course. The important thing to take from all of this is that there are various positions that an electron can take within an atom. And that position ultimately determines the average distance that an electron is from the attractive nucleus and other repelling electrons. That in turn affects the energy of the electron. So you should hopefully remember seeing energy diagrams like this before. What it's saying is that an electron that occupies this 1s orbital has a lower energy than an electron that would occupy a 2s orbital. And that makes sense because electrons in this orbital are further away from the nucleus than in this orbital. And being further away from those attractive positive protons, because opposites attract, causes the energy of the electron to increase and become less stable. And an electron is naturally going to occupy the position or orbital that has the lowest energy. And that brings us to the most important concept for this course. Just because the electron occupies a low energy orbital doesn't mean it can't be promoted to a higher energy orbital in a process known as excitation. It just needs to gain that energy from some source. That source could be light. We've already learned that all light has an energy, and if that energy happens to be equal to the difference in energy between two orbitals, then that light can potentially be absorbed by an electron, and the electron will take that energy and go to a higher energy position in the atom. And we call that process excitation. So let's write down the most important formula of the day, if not the entire unit. I am going to star this 3 times because that's how important it is. And I'm probably going to say this every lecture from here on out, so you absolutely need to know this. If the energy of light is equal to the delta E between levels, or orbitals, then light can be absorbed. Light can be absorbed. And we'll see as we go through this unit that this relationship here is the key to everything in spectroscopy. One last concept that I want to quickly show you that's also going to be very important is the electromagnetic spectrum, which gives different labels to different wavelengths and frequencies of light. And we can see that it's going from high frequency light waves to low frequency light waves. And so as frequency goes from high to low, so does energy based on those equations we learned. And in turn, the amount of energy that a light wave carries can cause different phenomena to happen within a molecule or an atom upon absorbing that light. But we'll get into these different processes as they become more relevant.